Okay, sorry for the interruption. So, as I was saying, we are going to discuss connection with thermodynamics, and this is the relation that we're going to derive. Okay, so in the earlier lecture, we discussed connection with thermodynamics, okay, through the relation S equal to K log omega, right? And this is the entropy here, and this is the what, total number of micro states, okay, and this is our Boltzmann constant. Okay, so this relation gap, connection between, you know microscopic, okay, details, okay, and our macroscopic observables, okay, or observables. So this is a very famous relation derived by Boltzmann, and this is the entropy relation, that relates to the total number of microstates. Okay, so this we are familiar with. Okay, now let us move ahead and try to connect to some other thermodynamic quantities which is of very importance to various applications, okay, namely the free energy. Okay, the relation I showed you here, it is this is Helmholtz free energy, okay, and it is related to the partition function. Okay, so this relation we're going to establish, okay, and I just reminded you of this because this is equally a good relation which connects the microscopic as well as macroscopic. Now that we have already learned about how to write down the partition function, we are ready to derive this relation to thermodynamics and the microscopic dynamics, but in a different language, in the sense that different kind of relation. Okay, let's just say, let's start with, say, partition function. Okay, so partition function, what is the partition function? C, okay, is written as summation r e to the minus beta er. Okay, so this is nothing but the sum over all the states. Okay, this is sum over all the states of the so-called Boltzmann factor. Okay, what I refer to is this e to the power negative beta er. Okay, beta as usual is 1 over kVt. Okay, so we have this relation at our hand. Now let's look at this way. Okay, here we can see that this energy R refers to some particular state of energy, so we don't have to worry about what it is. Okay, so in general, energy depends on some external parameter. Let's call that x. Okay, where x is our external parameter. Okay, let me write it as external parameter. Okay, and this brings us to the following relation for, or say, functional form of the partition function. Now z is now a function of this beta as well as this x. Okay, because energy depends on x, and thus z, the partition function, depends both on the value of beta, I mean the temperature. You could write temperature as well, but let's just use beta for convenience, and the external parameter x. Okay, this is our, let's say, first, let me put it as equation number 1. Okay, now what we do is, let's just take a, derivative of log of z. Okay, now let us take a derivative of log of z. Okay, uh, so let's do this. Okay, uh, as usual, see, now z is a function of two variables. Now let me write down the following: del log z by del beta, this is partial. Okay, and d beta, plus del log z by, now you can see already dx, I mean del x and dx. Okay, this is our expression. Okay, now what is this here? This is nothing but our negative of the average energy that we derived in the discussion of canonical ensemble, and here is the another term which is a derivative of the a derivative with respect to the external parameter. Okay, so in this, what we have to know is there is a relation that I have not discussed, but you can check it out. We can in fact show that this, let me just put it as sense. Okay, we can in fact show that this work done, which is a path dependent, is, or it can be written as the following. Okay, delta log z by delta x into dx. Okay, so this may be taken as your home assignment or home reading to figure out how this relation comes about. And if we plug in this expression here can be written immediately as beta d omega. Okay, so now let me just move to the next slide and say, therefore we can write this d log of z as negative e bar and del beta plus beta del beta. Okay, so this is one relation we get. Okay, let's put this equation number 2. Okay, now let's move ahead and do another trick. It's not a difficult trick, but the fact is we have to recognize the following. Okay, now let's do this. What do you get if you do this? E bar beta. Okay, this is nothing but E bar del beta plus beta del E bar, right? So this implies we can write negative E beta del bar to be, you see, you just take it on the other side, beta del E bar and minus del E bar beta, right? So let's just make use of this and rewrite the above expression. Okay, so now this brings us to the following expression. Okay, therefore, okay, this del log z is equal to beta del omega minus d E bar beta, okay, plus beta E bar. Okay, let us group the terms. What are terms which we can group together? You see, differential of this log of z, and take this on the left side, and we have plus beta E bar. Okay, and what is on the right side? We have beta in common, so let's just take beta, this plus, okay, Now you recognize what is this term? This is heat absorption. This is from the first law of thermodynamics. So we can write beta del. Okay. So we have a relation here. Okay. This is say 4. Okay. Now we have to make a recollection of the following. Okay, the entropy change is given by the del cube over T, right? Or this, in fact, you can write as follows: K ds equal to beta del. So what I've done is I've just on the right hand side, uh, so you multiply both side by no, sorry, you do like this. What I want to say is I want to write in terms of beta dq. So beta is 1 over kbt, right? So you multiply up and down by kb, this Boltzmann constant. So this is del s by kb Boltzmann constant. Oh, I have not used subscript b, so let us stick to k only, equal to beta d. Okay, let's just put this as equation number 5. Okay, so now we have to compare equation number 4 and 5. So we get the following, right? What do you get? So this will give us s by s by k equal to log of z plus beta e bar. Okay, so this is nothing but s equal to k times log z plus okay. Now this can be rewritten as follows. So this can be rewritten and you rewritten like this. Okay, kt log of z plus e bar. Okay, and e bar minus ds is kt log of z. Okay, so let's fix a number for this expression here. So this is equation number 6. Okay, again we have to recollect the definition of Helmholtz free energy. What is the expression? The Helmholtz free energy F is E minus ds. Okay, so if you compare, okay, compare this equation 6 and 7, we get free energy to be negative okay, I should put 1 minus here. Okay, negative kt log of z. Okay, so now you see we have successfully arrived at the relation what we displayed at the beginning. Okay, and this is a relation which also establishes connection between the microscopic details which is taken care by by the partition function, which is, sum over all the states, okay, and a macroscopic quantity, which is our energy or free energy, okay. So this is the relation of Helmholtz free energy in terms of partition function, okay. Now that we know the expression of partition function, we can directly make use of this relation of Helmholtz free energy. You can directly calculate. For example, in the previous exercise, we discussed about, say, about a system having two energy states, right? Say state energy defined by 0 and energy defined by, let's say, epsilon, right? And we also could or we in fact wrote down the partition function, which is simply, sum over all the states, okay. And for this system at a given temperature, which is nothing but the given a fixed value of beta, you can in fact write down the free energy. F is negative kb t log of the partition function. So you see, the entire exercise of the statistical mechanics at some point of time will boils down to calculation of, okay, will boils down to calculation of partition function, you see. So in the previous exercise of non-interacting spin model, okay, you could use this expression and try to calculate the free energy, okay. So this expression is very useful, but the essential point is you should be able to calculate the partition function. And the calculation of partition function, z calculation, is not always easy, okay. So what we discussed in the lecture was a very simple, most of the very simple non-interacting system, very simple. But you go a little bit closer to a more realistic description of the system, calculation of z already becomes complicated. So we will discuss those things in, say, Ising model, okay. So this model is normally taught in advanced StatMech course, okay, which I will teach for the pre-PhD course. But MSc students, if you're interested, you can attend, okay. I think you will be able to understand this, okay. This is not very difficult, but it will need some attention to get to the details, huh? So I think let us stop the theory description here.